Hi, in this video we are going to talk about Rabin Karp string searching algorithm. Let's understand the problem first. We have this text and a pattern. We need to find all occurrences of this pattern in the given text. These are the indexes of the characters in the text. So character A is at index 0, this is at 1, this is 2 and so on. Now we see this pattern. We can notice that this is present at index 3, right? At index 3 it begins and it has all the occurrences of the characters of the pattern in the same order. Then it also occurs at index 7. So our output is 3 and 7 separated by a space. Now let's see this text and this pattern. This pattern appears at index 0, then at index 1, then at index 2. So our output is 0, 1, 2. Let's now see this. We have this text ABCD and our pattern is XYZ. So pattern is not present in the text, so our output is not found. We have already talked about naive string searching algorithm, which is quadratic in time. Now we are going to talk about an optimized algorithm. This algorithm is also quadratic in worst case, but it works better in general. Like naive algorithm, in Rabin Karp also, we slide the pattern over the text one by one. But unlike naive algorithm, when we slide the pattern, we do not start comparing the individual characters immediately. What we do is, we use the idea of hashing. We compute a hash value of the pattern, which is an integer value, and hash value of every window of the text. If these two hash values, these two integer values match, then only we compare individual characters. That way, we save lots of comparisons for bigger patterns, especially for the bigger patterns. Let us now get an idea of working of Rabin Karp algorithm. Let's consider this text and this pattern. These are the indexes of characters in this text. We are going to slide this pattern over this text one by one, starting from index 0 to index 7. This is like naive algorithm, right? But unlike naive algorithm, when we are at current window of text, we do not compare all characters one by one. Rather, what we do is, we compare hash value of pattern with current hash value of text. If these two hash values match, then only we compare the individual characters. And if individual characters also match, then we print that particular index value. And then we move to the next window. We are going to use this term P for hash value of pattern and this term T for hash value of current window of text. Let us first understand Rabin Karp with a very simple hash function, although it's not a good hash function. We will see the problem with this hash functions later. So the hash function that we are going to use is simply sum the values of individual characters. Also for simplification, we are not considering ASCII values. We are considering these values. We are considering 1 for A, 2 for B, 3 for C and so on. And we are considering only 5 possible characters in pattern and text for simplicity of understanding. So what we do is, we first compute the hash value of pattern, and this hash value is 1 plus 2 plus 3, which is 6, right? 1 for A, 2 for B, and 3 for C. Now we slide this pattern over the text one by one, and we begin with this index I equal to 0. And at this index, we compute the hash value of current window of text, T. And what is this value? 1 plus 2 plus 4. We have 4 for T, right? And this value is 7. So we first compare these two integer values, 6 and 7. They do not match. So we simply skip this particular window of text. Now we move to the next window, and again we compare the hash values. What is the hash value of next window? It's 2 plus 4 plus 1, 7. And this value is 6. 7 and 6 do not match. So we skip the next window also. Now we come to the next window, and what is the hash value of current window? It is 4 plus 1 plus 2, right? Again 7 do not match. Then we come to I equal to 3. At I equal to 3, we have the hash value as 6. And what is hash value of pattern? That is also 6. So they match. Now we are going to match individual characters. We are going to match this A with A, then this B with B, then the C with the C. And since all the characters match, they are in same order, we print the output as 3, that we found the pattern at index 3. Now we move to the next window, I equal to 4. And for this window, we have the hash value as 2 plus 3 plus 2, which is again 7. So they do not match. Hash values do not match. We simply do not match the individual characters. Now we come to I equal to 5. And this is interesting. What is the hash value now? Hash value for I equal to 5 is 3 plus 2 plus 1, 6. Right? 3 plus 2 plus 1, 6. And hash value of our pattern is also 6. So what are we going to do now? We are going to match individual characters one by one. And these individual characters are not going to match. For example, you will match C with A, and at this point only you will realize that this is not a valid match. And this particular hash value match is called spurious hit. We matched the hash values, but characters were not matching, right? Now we go to the next window and we again compare the hash values first. Hash value is 5 here and our pattern hash value is 6, so they do not match, so we simply skip it. Now we come to 7 and hash values match. Now we match individual characters, A and A match, B and B match, C and C match. So we print this particular index 7 also as an output. So we get 3 and 7 as output. Now a simple question arises in our mind. We are doing sum of values in the hash function. This is again big O of M work if M is the length of the pattern, because every window is going to be of size M, and for every window you are going to sum the ASCII values and it's again looking like naive. But if you take a look at this, you can optimize this hash value computation. You can compute the hash value of current window by subtracting the ASCII value or value of the last character of previous window and adding the value of the last character of current window. And that's the main idea of Rabin Karp. And this is called rolling hash, where we can compute the next hash using previous hash in constant time. Here is expression for simple rolling hash. Here M is the length of pattern. We can compute hash value for window at index I plus 1 using existing hash value for window at index I by simply adding last character of I plus 1th window and subtracting the last character of ith window. For example, using this hash at index I equal to 3, we can compute the hash for 4. We can simply take this value 6, subtract this value 1 from it and add this value 2 to it. So we will have 6 minus 1 plus 2, 7. This is how we can compute the rolling hash. For a pattern of length 3, it might not be looking like a big optimization, but imagine patterns of lengths hundreds or thousands. We are simply doing one addition, one subtraction rather than traversing through those hundreds of characters. So this rolling hash can be computed in big O of one time using the previous hash value. We just talked about a simple hash function. This simple hash function causes many spurious hits, especially when the character set is small. Whenever you have a permutation of pattern present in the text, it's going to cause a match in hash values. For example, two words, God and Dog, they are going to have the same hash values because the sum of ASCII values of different permutations of characters are going to be same. To avoid this issue, we have an improved hash function. And in this hash function, we introduce a variable D. Instead of doing simply sum of ASCII values, we do a weighted sum where we multiply ASCII values or values with powers of D, right? So here I'm not using ASCII values. I'm using these values corresponding to the characters. So we multiply these values with powers of D. We multiply the first character with D square. So please note that there are 3 characters in the pattern. So I'm considering a window of size 3. And the first character is multiplied by the length of the pattern minus 1, right? So here the length is 3. So we are going to multiply it with D square. Then we multiply with D raised to the power 1, then D raised to the power 0. And that's how we get this hash value for this particular string. Similarly, we get this hash value for this string. D's value is 4. We multiply 4 into d square, then we multiply 1 into d, then 2 into d raised to the power 0, and we get this ASCII value. So now we have a better hash function which is using weighted sum. How do we ensure that this function is also rolling? How do we make sure that we can compute the hash function of next window of text using the existing hash value of the previous window? Fortunately, we have a formula here. We can get this function for window starting with index I plus 1 using the value of window with index starting with I. We subtract the first character of previous window, multiply by d raised to the power m minus 1, and then we add the last character of current window. That's how we get the hash value of the current window. Let's understand this formula with these examples. So we first compute the hash value t0 for the first window explicitly. I just simply use the above formula, above computation, to get the hash function for first window. Now to compute the hash function of the next window, I'm using this formula. And how are we using it? We have d equal to 5, t naught equal to 39, minus 1 into 5 square plus 1, right? And that's how we get the value 71. And to compute the hash function of this window, starting with t2, we use the value of t1. We do subtract the last character of previous window, 2 into 5 square, and add the last character of current window. So current window begins with 2, its last character is b, so we add 2 here for b, and we get this hash function. Now t3, again we use the existing value of t2, we subtract 4 into 5 square, the first character of previous window, right, and multiplied by d raised to the power m minus 1, and we add the last character of current window. This computation is actually similar to what we do in decimal arithmetic. For example, if you consider this text of simple decimal digits and you consider d equal to 10, m equal to 4, the pattern length is 4, and if we simply take the values of the windows, so the value of first window is clearly 1324. Now we need to compute the value of this window using the value of this window. So we want to get the value 3245 using 1324. How do we get this value? We are simply going to take the last 3 digits of this, right? Decimal value corresponding to last 3 digits, going to multiply it with 10, and then we are going to add 5. Right? That's what we want, right? We want 3245. Now, how do I write formally so that I can convert this number into this number? For that, what I'll do is, I'll take 1324 and I'll subtract 1 into 10 raised to the power 3 from it, right? Pattern length minus 1. So if you do the subtraction, what will you get? You will get 324. And if you multiply this number with 10, what you will get? You will get 3240. And now what all you need to do is, you need to add 5 to it. Now if you add 5 to it, what will you get? You will get, this number you will get as 324. Multiply by 10 plus 5. So you get your required number, which is value of the next window, 3245. You can consider these computations same as this computation. This is just in base 5. We have 5 characters. We have taken d equal to 5. Here we had total 10 possible digits. So we took d equal to 10 and we took the window size as 4. Here the window size is 3. And we are doing the exactly same in base 5 for these characters as digits, right? What we did here to find the value of this window using the value of this window. Let us now talk about implementation of Rabin-Karp algorithm. The code written here is a pseudo code for Rabin-Karp. This code is very close to C++ and Java codes. If you take a closer look at this code, you can notice that at many places we are doing computations under modulo Q, right? This is under modulo Q, this is under modulo Q, this is under modulo Q, and this computation is also under modulo Q. The reason for doing this modulo computation is when we are doing weighted sum of ASCII values of characters of a string, this number can become really large even for smallest things. So we compute this number under modulo so that we can store it in an integer variable or a long int variable. This q that we have written here is generally a prime number, and we would like to choose q as big as possible so that there are less spurious hits. Because if your prime number is small and if you're doing modulo under this prime number, you are going to have very few values as a result of modulo. For example, if q is 13, then the result numbers are going to be from 0 to 12, which is a very small number. And as per Pigeonhole principle, many spurious hits are possible. Okay, so we have computations under modulo. Let's now talk about this code step by step. The first thing that we do is we pre-compute this value, d raised to the power m minus 1 modulo q. We are going to use this value in this computation. So instead of doing this computation again and again inside a loop, we have pre-computed this value. Now we are going to compute hash function for first window of text and hash function for the pattern. And to do these hash function computations, we are going to follow Horner's rule. Let's understand this Horner's rule. So if you want to compute the hash function of the pattern, basically we want to compute this value. We want to take the ASCII value pattern 0. We want to multiply it with d raised to the power m minus 1. Then we want to add it with pattern 1 with d raised to the multiplication d raised to the power m minus 2 and so on. Now one simple way to compute this value is we initialize p equal to 0. Then in a loop we do this. For I equal to 0 we do this. For I equal to 1 we do this. And we run a loop for I equal to pattern length minus 1. Let's see what does this mean. After you have done this, your p value is going to have pattern 0, right? And after you have done this, your p value is going to have pattern 0 into d plus pattern 1. And after this, you are going to have pattern 0 into d square plus pattern 1 into d plus pattern 2. Alright, I'm simply substituting this value here, multiplying it with d, and that's how I got this expression. And this is the required hash function for a pattern of length 3. And this is the required hash function for a pattern of length 2. This is the hash function for a pattern of length 1. So this is how we compute the hash function for the pattern. And using the same logic, we compute the hash function for the text. So we've computed the first set of hash functions. This pattern hash function is going to be used everywhere in the comparison. And this text hash function is going to be used only for the first window. Now we run a loop for all the windows one by one. And inside this loop, we compare the values of p and t. If these two values are matching, then we compare individual characters. We run a loop for j equal to 0 to m minus 1. We compare the character text I plus j. We are at window I, so we need to shift by I in the text and with pattern j. At any moment, if we find that these two characters are not matching, we set the flag as false and break. If the flag remains true, we found the pattern at shift I. So we print I as part of the result. So this is normal sliding window one by one, sliding over the text one by one, and then comparing the pattern and text. If they match, then we simply print. Now we need to compute the hash function for next iteration. We compute the value of t using the previous value of t. And we use the same function that we just discussed. We are going to subtract this previous window's first character multiplied by h, and then need to add the last character of current window, and we need to do all these computations under modulo q. This is how we compute the hash function for next window of text. And please note that since we have subtraction here, this hash function t value might become negative. So to ensure that we have positive values, because we are going to compare these values here, we add q to it. To ensure that this is a positive value and both positive values compare to equal. Please note that if you have modulo computations, for example, modulo 3 minus 3 modulo 13 is equivalent to minus 3 plus 13 modulo 13, right? So this is 10 mod 13. So what you want is, you want 10 number. You do not want -3 because the other number is also positive. You want to ensure that both the numbers are positive. So when you compare them, they remain compared well, right? So that's the purpose of writing this condition. And this whole thing is written for I smaller than n minus 1. The reason is simple. We do not want to compute the next hash function for the last window, right? So we want to stop this computation for last window. That's why we have put this condition. So this is simple code which does pre-compute pattern and text hash functions first, then slides over the text, and for every window of the text, it computes the hash function for next window using the hash function of the previous window. Let us now talk about time complexity of Rabin-Karp algorithm. In worst case, Rabin-Karp's time complexity is same as naive algorithm, and the worst case happens for cases like this. If you see this text and this pattern, what are you going to do? You are going to compare the hash values, and hash values are going to match everywhere. They are going to match here, here, and here. And every time you are going to compare all the characters one by one. So that's how you get this time complexity. So it is like naive algorithm in worst case. In fact, it does more work than naive algorithm in worst case because it's going to require hash function computations. But on average, it works better than naive because you won't have such cases all the time. And if you have large patterns, you are going to skip many character matches that you do in naive algorithm. There exists better pattern searching algorithms like KMP algorithm, which work in linear time. The time complexity is quadratic here. But Rabin-Karp algorithm has its own applications. It is used when we want to search multiple patterns in a text. So what we do is, we compute multiple hash functions for all the patterns. We slide over the text. For every window, we check if the current hash value falls in or matches with any of the hash functions of the patterns. And if matches, we compare it with that particular pattern. So it is used practically when you have multiple patterns to be searched in a text.